Research and Engineering, and today we'll go through the just a normal presentation from the Flownex and its capability, and then we'll proceed through how it can be used in nuclear industries. So from first we can start from a small general introduction of Flownex and how the software will work. Then see. So I think my screen has been visible now. So Flownex is an one-dimensional simulation tool which is capable of solving thermal fluid networks, different type of systems, subsystems, as well as it has a built-in function for a component called the script or a library in which you can also modify and add your own functions or own calculations within it. So this software has been developed by MTech Technologies, which is a South African based companies in 90s, and it is among the few softwares which is nuclear certified by American Society of Mechanical Engineering in the year of 2008, and it has also ISO certification in the year of 2009. So it thus in this software there are a number of nuclear models has been built. One of them is the reactors for the South African power generation corporations, and the software has been verified and tested by also NASA, and the capabilities has been well recognized throughout the globe. The Flownex solver works on finite volume methods, and it discretizes the total systems into number of control volumes, and it then takes the Eulerian control volumes to formulate the equations. So the equations for mass, momentum, and energy conservation equations, which is one form of Navier-Stokes equations, is converted into surface integral form, and then a solver matrix is used to solve those equations, and the solution is based on implicit iterative pressure correction method. In this method, what it does, the solver will guess the initial pressure in first, and after guessing the initial pressure at that point, it is going to try to solve mass, momentum, and energy equations. So when these equations are being solved for that particular pressure, then it is going for energy conservation. Let's say it is not conserved, then the solver will try to change the pressure, and after changing the pressure, for that new pressure value, it is again try to solve those equations. So this process is iterative, and it will continue till we get the solutions. So the Flownex, this is capable of simulating for a different type of thermal and fluid networks like incompressible fluid, compressible fluid, two-phase fluid, incondensable slurry and gas mixers, different type of heat transfers, which is almost useful for any type of scenarios. Then small mechanical systems like gearbox assemblies, and electrical like some voltage source, current source like that. And it has also a specified DCS or digital control system libraries. So by utilizing that, you can perform automations and different type of logic and operations within this environment. So it is very handy when you are going to simulate a larger network in automated mode, or if you want to give any feedback like pressure or temperature feedback in order to achieve stability inside the system, then you can utilize these digital control system libraries. And it has proportional integral, and derivative controllers are there. So by utilizing this, you can add automation to the models. So the system can perform both steady state and dynamic analysis. So that might be any pressure surge type of analysis, any mixing of fluids, any heat transfers phenomenon, then choking, natural convections, different types of heating phenomenons. Then you can specify the conductions, and all the simulations can be performed in real time, and both steady state and uh, transient simulation you can also do. And if you want to optimize your network or any perform any parametric studies, these facilities are also included, in which you can uh, run different type of analysis like Monte Carlo analysis and parametric study to see the change in parameters and the total effect, whatever the effect is come upon the systems. So in this graph you can see there is a pressure surge analysis which has been performed, and it shows you the transient capabilities of the solver and how with respect to time it is going to calculate the pressure surge. So this is the graphical user interface. So in this interface you can see this is the drawing page. You can just drag and drop all the components up onto the screen, and in this left side you just have to give the inputs for those components, like whatever inputs this component is related to. And the top part is the solver tab, in which you have to perform the steady state operations, then transient operations, then you can perform the optimizer and the sensitive analysis type of operations. And here there is the error log. So if there is any error will arise within your simulation time, then the solver will highlighted that component, and by clicking it you can see which type of error is there. Like if you miss some inputs or if you miss the fluid properties like that, then it is going to highlighted those errors. So these facilities is very handy. Like say if you have a very larger network is there and hundreds of components are there, so individually checking each components it's difficult. So in that case you can the solver will highlighted you that component and you can go and rectify your errors. Apart from that, you can integrate these softwares with other softwares through API or open platform communications. So there are some pre-built APIs are there, like ANSYS Structural, ANSYS Fluent, ANSYS CFX, LabVIEW, MathCAD, Simulink, and AutoCAD. So these pre-built APIs you can directly link with those softwares, and if any softwares has the API configurations within that, then you can create your own API through either C# code or Python code. Then you can integrate the software with that software, or else you can communicate with other softwares like open platform communications. So open platform communications is a Excel and comma.csv file format, in which there is a specific format those values are stores, and any other softwares which is capable of reading the OPCs or CSV files, they can able to communicate with this software. So this open platform communication is useful when you are going to simulate a total system or plant simulations, in which the control system is from another company or another vendor, then you want to integrate with the Flownex. So in that case open platform communication comes into uh, help into that thing, so that you can able to communicate with this software with that other tool. Apart from that, you can also import different type of fluid database and material properties from NIST and RepProp. So you don't have to every time manually configure those fluid properties, gases, and other solid or any materials you want to specify. So some are available in these NIST and RepProp database. You directly import those values within this environment. So these are the Flownex users. You can see different IITs, NITs, then ISC Bangalore's, IGCAR, and different government institute are using this software. So now for nuclear applications. So in this Flownex, we can model the nuclear different type of nuclear reactors if you have sufficient data with you. Like say if you have the neutronics for that, then you can build the pressurized water reactor configuration. Then you can also build the heavy water reactor configuration. So if you know the neutronics for that, then you can apply it through any code, or in other language you have that pre-built like Fortran code, then you can communicate with this software through APIs. So all the neutron related data and the all the heat inputs and other thing you can build here within this environment, which will be go through in next some slide. And again, if there is pre-built libraries there in other software, you can directly import it into this environment. So this thing happened in from the last year, where the IGCAR has developed some their models, and they have built those models in the Fortran code. So utilizing this software, so and applying those API configurations, those Fortran DLL libraries has been linked to the Flownex environment. So it can perform the co-simulation with Fortran code, in which all the Newtonics calculation has been done, and all the flow related calculation and heat transfer related calculation has been done in the Simopact. Yeah, sorry, in the Flownex. So in this there are several aspects are there in the, so there are several aspects of that in the Flownex, where you can build your Newtonics model through programming or script, and you can also assign your control system within it. Then you can build your test reactors, different type of heat exchange models, like when the primary fluid is going to exchange heat with the secondary fluid, then you can perform the different type of safety analysis with that, and different type of accident analysis with that. So in control philosophy, then you can perform different type of plant transient response by utilizing the DCS libraries through scripting or coupling with the other third-party softwares. So in safety department or an accident analysis, you can specify the different relief valve sizing, relief valve operation characteristic, then passive heat removal analysis, then different type of circulations which may have associated with the circuit, then the amount of heat transfer you can calculate in a different type of heat exchangers, like cell tube heat exchanger or any recuperative type heat exchanger also can be built. Then there are also the flow related circuits can be built, which may be your steam side, like steam turbines, condenser, feed water heaters, cooling towers, and different type of valve configurations flow related you can also model within this environment. So so in this you can see this is the nuclear component in which all the Newtonian reaction has been integrated, and from this we are going to simulate those things. So whatever the model has been adopted, so that depends upon the point reactor neutron kinetics equations. So from this paper, they have taken the data of the neutron densities, as well as the different type of point the decay rates calculations, and the different type of precursor isotopes relative to different type of concentration. Those data has been taken from this paper, and from this you can see there are all the relations and all the equations which are present to calculation had been incorporated into the model. So for that, if I go to the model, so the model has been built as the sodium cooled fast reactor model. So in this sodium cooled fast reactor model, the primary fluid has been used as the sodium metals, which is operating in the liquid phase at a certain pressures, and it is going to exchange heat with the secondary sodium loop, and from that secondary sodium loop it is going to exchange heat with the water. So in case of steam generator, steam is generated by exchanging heat with the secondary loop. So in this study, we are going to see the effect of uh, yes, in this study we are going to check the system behavior by introducing the control rods within the reactor. So by varying the position of the control rods either in positive direction or negative direction, it means by putting it inside the fuel and removing it inside the fuel, then we can check the dynamic system behaviors and how the power generation and decay rate has been affected by it. So it is the models. And if I go to the Flownex, you can see it is the reactor model which has been made by from referred to that point kinetic neutron analysis. So here it is the primary sodium loop has been represented by this. So from this primary sodium loop we can see this is the component we are going to simulate for this reactor. So all the neutronic dynamics has been introduced within this script in terms of C# code, and from this code it is going to evaluate the decay heat, the total amount of fusion power, then fuel reactivity, normalized power, then the previous state, and the average fuel temperature and the total amount of reactivity. So if you want to modify those codes, like if you have any other codes, then you can also implement it here in this format. You just have to specify your reaction and reaction rate and all the variables which are going to be used to calculate all those reaction. Then you can also integrate the Zenon Poisson or uh, the amount of iodine generation throughout this cycle. So this model has been pre-built by a simple network like the point kinetic neutronics model, and from this it is going to calculate the amount of total heat generation from this model. So this heat has been taken out through this cycle, and from this cycle it is going to exchange heat with the secondary sodium loop. So if you can see, this middle portion represent the secondary sodium loop side, and from this secondary sodium loop side, here it is going to exchange heat with 1, 2 and 3 heat steam generators. So before we go through the model, let me go through a quick review of this the component which are available in this component in this library. So first is this script component in which you will get all the calculations, and if you have the nuclear model, then there are different type of nuclear calculation script are there. So you can directly drag and drop those components onto the screen, and it is going to evaluate and integrate with your system. Apart from that, in the flow solver department you will get different type of chemical reactions, any type of combustion reactions are there. Then in order to simulate the different type of pressure vessels or containers, there are several components are there, like phase change, like two phase tanks are there for uh, simulating the phase change phenomenon of the fluid. Then you will get the open container to simulating a open container which is directly open to the atmosphere. Then it is closed container known as the reservoirs. Then if there is any pressure surge and you want to accommodate that, then accumulator function is that. So there you can specify the gas volume and the total amount of expansion possible, and according to that it will going to reduce your surge. Then you can specify different type of losses which is going to happen inside the flow pipes. Then that is the flow resistance component. It is just like to give you the resistance inside the flow. Then another is the empirical relationship of the flow. It means if you have any pressure loss data are there and you want to simulate the pressure loss through a flow network according to your data, you can put your functions like viscosity functions and density functions within this this component. So there are different type of flow meters are there, then different type of discharge nozzles are there for like exit thrust nozzle and normal nozzles. Then you get the ducting component, then flow distributor and heat exchangers. So in this heat exchanger part, it is useful for simulate the thermal fluid networks. You will get the evaporating cooling heat exchangers like a cooling tower and bulk air coolers. Then you will get the evaporator then you get the fin and tube heat exchangers, then primary and secondary heat exchangers, in which you only have to specify the overall heat transfer coefficient and the area for the heat transfer. Then you get the plate type heat exchanger and selective heat exchanger. So these are useful when you are going to model a large network. Then if you want to minutely model any network, you will get small heat transfer components like the conduction components, convection components, then cross conduction, film convection, and fluid radiation components. So utilizing this component, you are going to model minutely or details model of a flow network. So like this, in this model we have utilized the distributed heat source component. So distributed heat source component, what it does, let's say there are q amount of heat is going to pass and it is going to transfer to the fluid medium. Then according to the heat generation, it is going to distribute those heat generation in a fractional manner throughout the length. So in case of reactor, there are different zones for the heat generation. So according to that, those zones and the amount of heat generation from each zones, they factorize that and utilize this component to model. So instead of acting as a single unit source, so these fractions has been used to represent a different geometry of the reactor, and from those different geometry, variation amount of heat is going to generate, and those heat is going to feed to this cooling medium, or in case of molten sodium. So apart from that, you will get different type of boundary condition you can specify. Then there are also restrictors for simulating the flow restriction inside the part where the discharge coefficient is come into the picture. Then you will get different type of intake, you will get the different type of rotating components, like these are useful when there are small cavity flows are there or any small network flow is there. Then you can specify those, like different type of sealing, different type of rotating channel, different type of cavity you can specify. Then you will get the turbos and pumps. So these are useful to maintain the flow, and you can specify the pumps curves, compressor curves, and turbine curves throughout this, and you can model the network. So in this model, we utilize a basic centrifugal pump, in which if I double click it and open it, we can specify the total amount of head it is going to develop, then the maximum volume flow rate at its maximum efficiency point, then the speed at maximum efficiency point, and the number of stages. So if you combine this and let's say there is a differential flow rate is going to be maintained, then you can utilize the variable speed pumps. So for these variable speed pumps, you can always create your own pump curves, like mm, here let me show you. Okay, so from this you can specify your own pump curve within this environment, in which you have to specify the volume flow rate versus the pressure rise. Then you can specify the hydraulic efficiency and net positive suction head data and the reference density, and you can assign this curve according to your need throughout this network. So in this network, as I have mentioned, this too is also the heat transfer elements. So these are the composite heat transfer elements. It means you can specify the different layers. So let's say there are different metals layers are there, like you have the tin, you have the um, lead layer is there, or you have the steel layer is there. Then you can specify here, you can add the layers here, and you can specify the materials. So you can simulate those things, and these two layers has been here represented the axial and the upper and the lower reflective components for the reactor. So the fluid which is utilized in this model is the molten sodium. So this fluid has been developed in this uh, Flownex environment. If I go to the fluid tab, here you can see by right click it, you can always create your own fluid. So if I double click the sodium fluid, you can see there is a window will pop up. Here you can specify the fluid properties like the compressibility of properties, then the molar mass, then the density. Then you can specify the constant density, or you can, if you have any equation script is there, then you can also always specify the variable density according to the temperature. So similar fashion you can specify the viscosities either in tabular manner or any equations, polynomial equations you have. Then you can also specify the conductivity of the material, then the heat capacity of the materials. So in this it is in tabular form, then you can also specify the constant form also. Then you can specify the entropy, the bulk modulus of the material, then the surface tension, the vapor pressure, and if it's the combustible mm, fluid, then you can specify the combustible and the reactant within it. Okay, so this sodium liquid which has been created has been used. So if I right click it and go to the assign fluid tab, then you can see this sodium liquid is going to used here. So in similar fashion, this is going to circulate through within this circuit. And if I open you this image, you can clearly see the pump is going to circulate the liquid sodium throughout the core, where the liquid sodium is going to gain the heat from this reactor, and from this reactor it is again going to this heat exchanger, and in this heat exchanger it is going to exchange heat with the secondary sodium loop. And after um, losing heat to this heat exchanger, it is eventually cooled down and it is going to this. So it is both the forced circulation as well as the natural circulation phenomenon is going to happen in this primary loop. And after exchanging heat with the primary sodium cycle, the secondary sodium is going to gain heat and it is going to circulate in forced convection, in forced circulation through this loop. So from this, your water and steam generator or water loop is connected, and it is going to gain heat from this secondary sodium cycle, and eventually you will get the power output from this as per the Rankine cycle. So this same thing has been modeled here. So it is the primary loop and it is the secondary sodium loop, and this exchange heat with this water loop. So you can see for this primary loop circulation, one pump is there, sodium pump is there, and for secondary sodium loop circulation, for secondary sodium pumps are there. So these to maintain the flow of the secondary sodium loop, and it is the steam generator in which the water is exchanging heat. So for the primary loop, the sodium flow rate is maintained at 14,550 kg per second, and for each sodium secondary sodium loop the flow rate is maintained 5,500 kg per second, and the water loop and the flow rate is maintained at 700 kg per second. Okay, so from this model, if I try to solve the steady state, you can see the solver is trying to solve. And if I go to the advanced tab, you will get the amount of convergence is obtained from the solver. Here we will get the pressure solver, continuity solver, and temperature solver convergence. And when it is shows 100%, it means your network has been solved. So now our network has been solved. If I go to this heat transfer element and drag out the property, you will see the total amount of heat transfer and all the heat related parameters and the convection coefficients and the amount of convective heat transfer, amount of radiation heat transfer throughout this result window. Okay, now it is for the steady state condition. Let's say I want to perform the transient conditions, and I want to monitor what is the effect of transient and the neutron rods when it is going through these reactors. So for that, let's say we run this model. So as you can see from this, the first graph is between the total reactivity and the average inlet temperature for the primary fluid cycle and the total amount of heat is generated from the nuclear core. And the second graph represents the total amount of temperature. One is for the primary side and another one for the secondary side. So blue one for the primary and the red one for the secondary. So let's say this is the neutron rod control is there. So it is now in the neutral position. If I remove this neutron rods, the absorbing rods from this reactor core, then the reaction rate or the total reactivity will increase, and as well as the total amount of power also get increased. So if I put it down, then it is going to reduce the total decay rate. So if I open it, uh, and it is drag it to the upward, you can see there is a change in the total amount of reactivity, and that is going to reflected within this system. And you can study the system dynamically according to when it is going to run in transient conditions. So both, always you can perform both your real time and as well as the transient condition within it. And if you want to specify any other reaction or conditions within this transient setup, then you can also perform it. For that there is a provision, like say if you want to anything add for this um, what I can say, if you want to add any variations within these systems, then always you can go to the configuration tab in this action setup. Then you can create a scenario. In this scenario you can specify the change in temperature, change in pressures, or change in any parameters. And when you run the transient and specify the time limit within it, then the total, the variation of the system is going to reflected within the model. So in this way you can calculate the total amount of heat generated throughout this system, and after that heat generation, this heat is eventually transferred to any cooling mediums for power generation purpose. So in this case it is transferred to the steam water cycle, in this case the water cycle. So you can integrate another water cycle with this network, or by data transfer link or any medium you can transfer the total amount of heat transfer to the water loop. So let's see. Heat input logics. So it is the total water cycle has been modeled. So here the heat is going to added in this water cycle. So it is the representation of a modified Rankine cycle. So here from the reactor heat is input from this boiler and this superheater and the reheater. So whatever we saw earlier from that reactor model, that whatever heat is generated from the reactor core is transferred to the secondary loop, and that secondary loop is transfer heat to this the water steam water cycle. So from this steam water cycle, it is going to utilize to generate steam. It is the steam generator, and from this steam generator the steam is going to flow the high pressure turbine as well as the intermediate turbine as well as the low pressure turbine. So these are the control which has been used, and I have previously mentioned that there is a DCS library is there. So utilizing this DCS library, you can model the automated controls which is going to regulate your flow parameters within a cycle, as well as the labels in different type of drums, and all your system can be operated in automated manner. So in this case, that control has been utilized to maintain the flow rate to the turbines, and from these turbines bleed are also taken out for the regenerative heating purpose in order to increase the plant efficiency. And the steam is again reheat from the reactor heat and again expanded to the intermediate as well as the low pressure turbines. So it is the two-phase tank in which the condenser model has been done. Since the water is losing heat and changes, giving its latent heat to the other medium, the cooling medium, that has been modeled into two-phase tank. So here the air injection as well as the air leak as well as the vacuum cooling all has been modeled and put in the automations. And from this condenser, the pumps are utilized to circulate those flows throughout this network. So this is the deaerator, so removing the incondensable from throughout this network, and from the here you will get the feed pump, and it is going to again pump the water to the steam generation by completing the cycle. So all the valves and the speed control mechanism of this cycle has been integrated with the model and with the DCS system. So let's say I go to the visual tab and I run the system. So as you can see, it is the complete model, and all the heat generated whatever in your reactor side, and then it is transferred to your steam water side, and from this steam water side eventually you will see different parameters from this cycle which are running in the transient conditions, and those power generation is fed to the grid, and you will get the real-time tracking of different pressure and the level in different components of this cycle. So here you can determine the condenser pressure, condenser level, then the boiler or the steam generator pressure as well as level, then you will get the feed water pressures and level, then the generating power, the amount of total steam flows, then the fraction of valve or control valve opening, which you can see. Unfortunately I can zoom it more, but you can see those values are changing. It means the control is taking into account of the flow to regulate the flow and to regulate the power, and by following those power and flow requirement, it is going to vary the opening of the valves. So DCS or the digital control system, what I have mentioned earlier, comes into the play into the pictures to perform this type of transient analysis throughout this network. So let's say I am going to change some parameters, like say controls. Okay, so here the total graphical representation of the total network. So it is the cycle in which it is going to gain heat from the reactor, and it is the line diagram, or you can say the heat balance diagram for the total complete network, where it is going to generate the powers. So all things has been now done in the transient cases. So you can perform, as mentioned earlier, you can both perform the steady state as well as the transient simulations throughout the network. So it is all related to this heat transfer models, in which you will get the reactors model, And apart from that, let's say your cooling medium is not the steam water cycle. Instead, you will prefer the hot gas cooling medium, or there is a gas is flowing through this cycle to carry out the reactor heat. So in that case, you can also model those compressors as well as the turbines, which is going to connected with this reactor components. So for that, you can see the heat is given to this component here in terms of megawatt, and the helium gas is flowing through this network, and after gaining heat from the reactor core, the helium gas is going to expand in the um, high pressure turbine, and this high pressure turbine is connected with the high pressure compressor, which is again compress that expanded helium. And after expansion in this turbine, it is going to the low pressure turbine, and this low pressure turbine, it utilized for power generation purpose. In this case, it is not connected with the generator, and some part of this turbine power is going to utilize for the low pressure compressor. So after expansion in this low pressure turbine, it is the heat uh, recuperator type heat exchanger is there, which is going to exchange it heat with the incoming or cold helium, and it is after losing heat, it is again go through the intercooler, in which it try to reduce its temperature and increase its density, so the compressor process will be easier. And after that, the low pressure compressor is going to compress, and after the compression, it is again going to the intercooler. So here the heat is removed to the cooling medium, and after the intercooler, it is going to the high pressure compressor, which is directly connected to the high pressure turbine. So from this high pressure compressor, it is going to compress to high pressure, and this mm, uh, higher pressure fluid is going to exchange heat with the incoming from this turbine flow, and then it is going to the reactor again, so completing the cycle. So it is for the gas circulation cycle for this reactor. So another facilities for this software is you can also optimize this cycle. So in this case, we have optimized this utilizing the sensitive analysis setup. So if I going to expanded this tab, you can specify the parametric studies, as well as you can specify the Monte Carlo analysis for this software in this software. So here you can see there are different parameters are there, and we have to specify those values like low values and high values, and within these values your system parameter is going to vary, and this is the result you want to see. It means by varying those parameters, whatever the effect is going to affect the systems, and these are the system parameters. So if you perform those sensitive analysis study, then the solver is going to perform those analysis. Just to wait a little moment. Then you can see the results of this sensitive analysis. Here they are the independent variables. It means those variables which are supposed to be varied, and it is the dependent variable. It means by varying those variables, what are the effect are coming upon these variables. So these are in column format. For this 1 2 3 4, you will get 1 2 3 4 columns, and this is the number of iterations or runs, and for the results 1 2 3 4, you will get the last four columns 1 2 3 4. So you can see from this there is a variation is there from this boundary conditions in this case, or any independent variable. So those has been reflected, those changes has been reflected through these parameters. So by seeing this you can see by within by which range your system should operate in order to get the least variation from the network. So this is very handy in order to optimize your network, or any types of different type of analysis you want to perform. Those things comes into very handy within this environment. So as I have mentioned earlier, this the natural circulation phenomenon also happening inside this reactor. So for natural circulation, the software has also the capability to model the different type of different natural circulation phenomenons, in which the driving factor is the change in density. So when the fluid is going to take heat from any heating medium, in this case the reactor, it is going to uh, uh, it is going to in the density variations. So due to the low and high density, there is a flow is going to maintain within this cycle. So for that, if I open another model, you can see it is just a normal boiler in which the natural circulation is happening. So from this heating medium, you will get the heat transfer to this boiler, and from this boiler the water is coming through from the feed pumps, and it is going to this steam drum. And from this steam drum there are pipe arrangement are there, you can see those are the downcomers and those are the riser tube. So downcomers are those pipes in which the high density or the water is going to flow downward due to the effect of gravity, and it is stored into this small tank. And when it is going to heated from this any heating mediums by heat exchanging with this, it is eventually reduce its density. So due to this density variation, you will get a flow throughout this cycle, and this is also known as the natural circulation. So in this case you can see there is a flow rate of 218.994 kg of flow is maintained due to the heat transfer from this heating medium, and without utilizing of any pump or any external factors, only the elevation variation is there. So the steam drum is located at the elevation of 45 meter, and the lower drum is located at the elevation of 15 meters. So there is a 30 meter of difference is there, and this heat is the driving force to overcome this 30-meter heat and maintaining the flow within this natural circulation network. So same thing is happening inside this pressure. It's a sodium reactor, and you can also show this natural convection phenomenon within this network also. So the Flownex comes with several types of nuclear modules. So if you want to perform any nuclear analysis and nuclear calculations or any neutral links analysis, then we can always purchase from this Flownex regarding the nuclear models. Or if you have any sufficient data, or you develop any neutronix models yourself, you can implement those models within the script. So this entire script has been written in C sharp format, in which you have to specify the properties and different types of parameters. In this case we have specified different constant for the rate of reactions. Then you will get different it is the time dependent, since that is why you can link it to the solver time. Then you can specify the control rod data. So In this case, it can act as a matrix format in which whenever you get data, it will plot those into Cartesian coordinate format, and according to that, your control rod movement will be maintained. So here, the time dependent different type of rate of change of properties has been introduced within this in this coding format. Then this code is generate these results. So whatever you can write your own code within this environment, then you can always compile those codes, then execute those codes to see the values, and you can directly configure and relate those values to the flow network through the data transfer link. So if I double click it and show you the properties, here you can see the total amount of power can be connected to the as a heat input to the flow network. So these type of flexibilities and modeling you can also do here. And if I go to the import tab, I'm trying to set. Yes, in this help tab you can see there are different API configurations are there. So let's say you built any of your model in MATLAB code or in Python code, then you can directly link with this software, the flow solver, with those codes. And then that I have mentioned, there is also a OPC is there. So this is the OPC server connection is there. So if you have any OPC server pre-installed, then this is going to communication with that server. So here you can always specify the location of the server and server, and you can press open. Then it will create a virtual environment through which this software can be linked with CSV file with any other OPC compatible software. So this is all regarding the modeling capabilities, and in the nuclear whatever you can model. So anything specific you want to ask, or anything specific you want to model, now you can ask me regarding that. Hello.
Chakravarti sir, Amitabh sir, Mithun sir, please reply.
Yeah, hello, you can hear me?
Yes, sir.
Okay, so first I want some clarification. Like you didn't mention if the software solves in 1D or 2D or 3D.
Sir, during the introduction part, I have mentioned that this software is works on 1D in terms of
1D. Okay,
yes.
okay,
So let me explain a little bit.
yeah.
So it acts as 1D in case of our fluid networks. It
Okay.
means if you are going to model any flow systems, then
Mm-hmm.
it acts as 1D.
Okay.
So when you are going to model the heat transfer elements, like
Hmm.
say, then you can both model it into the 2D as well as 3D. Because if
Only for the heat transfer part.
yes, so if I go to the library part, and here you can see there are several heat transfer components are there.
Yeah.
Okay, so these components always act as in one direction, but you can always connect it into in three dimension. Like say, let me zoom it bit little bit. Here one component is connected like this, so it is for the one dimension. Heat can be transferred from this to this point. If I put like this, it is become the two dimension.
Okay.
Okay.
Okay. Like that. Okay.
Yes. So if I put like this, it is represent the z direction. So
Okay.
this heat transfer you can perform in any direction you want.
Okay. The other question that I had is, say you said that we can code our own reactor
Yes.
kinetics
Yes.
models, right?
Yes, sir.
So if we suppose want to model want to include models other than reactor kinetics, like say heat transfer models or say radiation models, like
Yes, yes,
is
sir.
that possible?
Yes, you can actually do it very easily. So
Okay.
let's say there is one component known as the quick script company is there. So you don't have to write the entire code here. Okay.
Okay.
So let's say you want to convective coefficient. You just specify it h, then you specify it as input or result, whatever you want. Then it is the convective coefficient. Okay.
Okay.
So you can see it is already added inside this here.
Yeah.
Uh, so here you only have to specify the relation, the
Okay.
convective
Understood.
coefficient relation within it. Then you execute it. Then it is directly
Yeah.
connected.
Understood.
Okay.
Understood. Understood. Okay. Okay. It's fine.
What is the recommended system configuration?
Yeah. Yeah. That's
Uh,
another question.
yes. So this system can be run in a low configured system like a dual core system or a dual core two thread system. You can run it, and in 4 GB RAM it can also run. But for efficient running, you can always prefer the 8 GB RAM. So no graphics requirement is required for this software. So there is another option. If I go to the setting and goes to this statistic, sorry, go to the, yes, go to the configuration. Here you can see, irrespective of core and system, you can always assign the load of the solver to the number of threads and cores. Okay, so if you have low specific system, then you can reduce this system count. Then if you have a multi-core system, you can increase the system count. You can specify the number of parallel tasks within the cores. So it is variable according to your system. You can configure the solver.
Means, sir, basically you should have a 8 GB for
Yes,
good level of running.
yes,
16 is recommended for
yes,
fast
yes,
work, but 8 GB you should have.
yes. Nowadays, 8 GB is the minimum requirement for any work. So that should have, everyone should have that amount of RAM.
And core i3 processor?
Excuse me, sir.
Uh, i5 you
Core i
can get i5. i3 also it will work. It's not like it will not work.
Yes, sir.
i3 or i5 you can anything take. No problem.
You can even work it at dual core. You will get some less performance, but it will run.
What
It will
is your recommendation?
take a larger some more time, but it will work run.
Yes, recommendation I can say you prefer the quad core processor with 8 GB RAM.
Okay.
Can we get a trial version or for 3 months or 6 months?
Uh, for
So
that,
that we'll have to ask to our management because trial version of this commercial license means you can say research license. I don't think our management has given to anyone, but we will see that. You just we'll see afterwards. We'll speak to our management.
At least 7 days or 15 days you can give no.
Anyway, but sir, we will give
uh,
the trial version.
yes,
We will provide a
so
training for that because
that
directly
can
you
be
cannot.
possible actually, but we have to talk with management, and if the possibility is there, then we can do that.
Yes.
Okay, okay, okay.
So I have another question. Say, suppose we are simulating one whole reactor model,
Okay,
and suppose we are simulating for one day. I mean,
okay,
not real time. I mean, we are simulate this. We are simulating for one day.
okay,
So, what? Say, suppose we are using your recommended system configuration.
okay.
Then, how much time will it require for the simulation to get complete?
So you want to
Just
perform
an
the
estimate.
transient? You want to perform the
Yeah,
transient, or
transient. Yeah, transient.
so uh, so let's say, so if I go to the solver tab uh, in this scheduler, you can always specify the time step size.
Yeah, I
Okay,
understand that. I
okay.
understand. I'm just
So
asking. Say, suppose you
yes,
have a
yes,
time step size of 0.1 second, right? Or
yes,
say you can take 1 second time step size.
Yes.
What would be the time estimate in I mean real time estimate for the simulation to complete?
Actually, it is instantaneous. It
Okay.
means, say, if you model correctly and all the parameters are fit correctly, so you can see the instantaneous variation is within the model. So
Yeah,
what?
that is true.
Yes.
I understand what you are saying. We can get instantaneous data. What I am
Hmm.
asking is how much time will it take to simulate a complete day of the reactor operation?
Uh, if you want to make it fast forward mode, then it can be done within 9 to 10 hours.
Okay, 9 to
But
10 hours. Okay.
yes, and if you want to real time, it will take exactly 1 day.
Okay.
Okay, so that
Okay,
depends
understood.
upon the,
Understood. Understood.
yes.
Any other questions, sir?
How extensive your control modeling?
So so let me show you the control library.
Hmm.
So here you get one library is called the distributed control system. So here the first is the analog components. In these analog components, you will get the controllers. You will
Hmm.
get the proportional, integral, and derivative controllers, and you can feed your feedback rate, your proportional, integral, derivative gains within the system to maintain the system stabilities.
Hmm.
Apart from that, you will get the different type of filters. It means the rate limiters. It means the how fast the system will going to change. Then the derivative rate of change. Then the delay integrators you will get. Then you get the analog functions like multiplication, divisions,
Hmm.
and modular divisions. Then clamp the signals, wavefront generator, weightage average, all types of things you can also perform.
Okay.
And you will get the switches are there like the toggle switches. Then
Hmm.
1 bit switches means it is going to store 1 bit operations, and if the signal coming and it is going to change the next bit, then it is going to vary the signal in further. So you will get the compound properties. You will get the digital components like the digital counters, which is going to count between 0 1. Then digital logics, all types of gates. You can
Hmm.
say anything, whatever the controls which are utilized in the real plants, those things can be emulated and simulated through this environment.
So I'll give you a scenario. Suppose we have reactor regulating systems in
Yes.
nuclear power plants. Okay,
Yes.
and they got both. Neutron flux measurements and other measurements also.
Yes.
Like you have also step back, setback controls, and all these things.
Okay.
Suppose I want to implement a regulating system with Flownex.
Okay.
How shall I go about it?
So let's say your regulating system must have taken some feedback from the properties like your pressure or temperature properties.
Correct.
Okay. So that properties you can see from any node of the system. Let's say if I click any node of the system and go to the result tab, you see the total pressure and the temperature at this particular point. Okay.
Hmm. Hmm.
So you can take this temperature or pressure as the feedback,
Hmm.
like the and you drag and drop a pressure integral controller,
Hmm.
and here you will get a data transfer link. Okay. So from this data transfer link, if I connect it, a windows will be pop up. Then you can drag this total temperature or pressure parameters to the
Hmm.
process variable. Process variables means which is going to vary, and a set point is what point or which parameter you want to maintain. Okay.
Hmm.
So then you have to specify the different gains or the feedback gains you can say. So this system is going to evaluate the error, and it is always try to reduce that error by the equations, the error equations, which is the function of both proportional, integral, and derivative functions. So in sinusoidal manner, or you can say in decay manner, it is going to try to balance the system. So that thing has been done what I have shown you in this
Correct.
model. in this transient model. Okay.
Okay. But what about neutronic feedbacks like the neutron flux?
Yes. So for that neutron flux, you always have the provision to subdivide this neutronic script. Okay.
Okay.
So if instead of single script or fixed neutron rate, if you can add two script, let's say one is for the result, it means the neutron flux, and another the variables which affect the neutron generating flux. Okay. So if I put this, let's say,
Can I? I have to interrupt once. Can I simulate multiple detectors? Like nowadays they are using something called a flux mapping system. Means, say from multiple locations inside the core, they are measuring neutronic flux. So
yes, yes,
that's
yes, you
possible.
can. Yes, sir, you can. It can be possible. So let's say it is the distributed control system. Mm, uh, let me so here there are sub elements are there. In this case we have three sub elements. Okay. So let's say there are multiple systems, you are saying that there are 10 or 5 probes are
No,
there.
maybe that number runs into say 130, 140.
Okay. So if that is 130, then you can map those by selecting this increment size. It will be uh, extended up to 130 or 140. You can connect with the script that we already did in the IGCAR. We mapped those intermediate parameters with the script, and by utilizing it, it can going to map all those parameters. You can even represent it visually through the visual library whatever present in this environment. So that is also possible.
Okay.
Yes, sir.
Hmm. I think for educational institutes, the licensing cost is less, isn't it?
Yes, in educational institute you will get less license, less cost as compared to the commercial license.
Aranak, if you want to ask anything else?
No, sir, I don't have any more questions.
We are getting academic version or professional version, something, or you're
Sir,
differentiating
there
us
is
with
a
us.
two types of version. One is uh, one is that commercial version, which is a commercial license, and for the academics for doing the research work, we have a research license.
Okay,
So
okay.
research license also comes in the one user bundle package, and there is a one also license name as a academic license. But in academic license, you don't have a rights to publish paper or any other commercial activity or research activity. So there are three types of licensing. Academics, one is research, which is a bit subsidized as compared to a commercial license, and one is commercial license. So for doing your kind of work, you will require to have a research license with you.
No,
Okay,
please,
okay.
please clarify. If I want to publish a paper, what I have to do based on your
Research
simulation?
license. Research license.
Okay.
Okay.
So, Aranak, do you have a quote already from them?
No, sir.
So get a
Nothing.
quote from them.
Academic
Yeah.
license comes in the bundle. Research work like the work right now what you have seen, and because
Research
academic
license.
license will be restricted to doing this work, and there is one commercial license. Commercial license and research license are equal license, and only the difference is that there is a costing difference because commercial license we are providing in the form of a research license to educational institute.
Hmm.
Okay.
But our basic aim is to publish, isn't it? Do research and publish. Then,
Yes, so research license is there for the research work for the academy for the educational institutes.
another thing, is there a perpetual license or it's a yearly renewal?
Uh,
Research is a perpetual one.
Okay.
Yes, academics has for research work the perpetual license. Okay,
Okay.
sir.
Okay.
Yes.
But one thing is that you are telling that NASA has vetted your system, but NASA is not doing anything on nuclear, isn't it?
Yes, but I'm not telling about that. It is American Nuclear Society certified ASM.
Okay, okay.
Okay, NASA utilize it for their experimental purpose for nuclear fuel rocket. One is
Oh,
there, so for that they are using it.
I think
Any
you
other
can
questions?
send a research license code to Arannak, huh?
Uh,
Okay, sir. Definitely,
okay,
we'll send to the.
And let's see how feasible it is.
Yes, we'll send it to
okay,
Aranya, sir. You just shoot me, Aranya, sir.
Yeah, yeah.
Please give me the a short one liner or two liner feedback for the today's session, how you liked or that, and please request in that mail also
Okay,
to
okay,
send the code for that. So we
okay,
will
okay,
get the research license pricing for our from our management.
okay, okay. Fine, fine,
Okay,
fine.
sir.
What
Thank you.
licensing does IG car have?
IGCAR have one is their research license and one is commercial type of license in which they are performing their pressure surge analysis,
Hmm.
and in another one they are developing their nuclear type what is connected with the photon code there.
Okay. But we'll be using either MATLAB or say Python.
No, that is the provision. If you have pre-built model within those languages, then you can directly connect it. So no need to develop another model in this environment. But
Mhm.
if you want to ground zero or from scratch, then you can model your model from this environment also.
Okay. I don't have any further question.
Okay, sir.
I also don't have any other questions.
Okay, sir. Then we will wind up our session.
Mhm.
I hope every doubt is clear. Thank you very much for your time, sir.
Okay, fine.
Thank you very much. Please give the feedback, Arin sir,
Yeah,
and
yeah, sure.
send me the request for the quotation. Okay.
Yeah, yeah, sure. I'll do that.
Thank you very much. Thank you.
Okay, sir.
Bye.
Thank you, sir.
Have a good day. Have a good day. Good night.
Good night.